Hi, I'm Bruce Clark, General Manager of a.i.tek. For over 50 years, a.i.tek has been providing reliable, predictable, cost-effective monitoring and control devices for some of the most demanding speed sensing applications on planet Earth and off. a.i.tek started life as Airpacks, a small industrial division of Fortune 100 companies. We are now privately owned, boasting all of the quality systems of those larger companies and the personal service and entrepreneurial spirit found in the best small companies. We are AS9100 ISO 9001 certified, and our sensors are made in the USA. I hope you will find the following training helpful in gaining insight into a.i.tek, the company, its products, and numerous applications we serve. Thanks for your interest in a.i.tek. Hi, welcome to the next installment of the a.i.tek Instruments Profile Training Series, Active Speed Sensors. Here we're going to discuss, if you've looked at it, you've probably seen the passive already. If not, there's another module that you can go check it out. Here we're just going to kind of take a look and explain, the speed sensors bridge the gap between the mechanical and the electrical world. What used to be done by a mechanical governor is now done by a speed sensor. They report or they produce a frequency proportional to the speed of the target. That's then interpreted by a tachometer instrument such as what we offer, or other input device that the customer has either developed or purchased. There's two basic technologies. Again, you can learn more about the VR. It's got a sinusoidal output. It's a two-wire device, and it's a simpler device. It's been around for a very long time, very mature. Again, we're going to focus on the Hall effect, or the active sensors in this particular module. It's a three-wire device, so it adds an extra wire. So you can see there's a power and a ground, and then there's an output. And instead of a sinusoidal output, there's a square wave output. And that square wave output better interfaces with many different electronic, logic circuits and that type of thing. All right, so again, Hall effect sensors, also known, I've got listed here as zero speed and active sensors. They're not all zero speed, and I guess that would be kind of the first point to address, is that a.i.tek makes zero speed active speed sensors. So some of them may be offered, we're showing here from zero speed to 15 kilohertz. The zero speed, really the definition best would be the lowest increment of speed possible. We will faithfully produce the target. We'll give you a pulse. So if there's 10 minutes between each pulse, we will faithfully reproduce that, and we'll be providing a pulse every 10 minutes. There are some speed sensors that are not zero speed, and what they do is they'll limit it. It's usually a fraction of a hertz or something like that. So it's not zero per se. So the heart of the Hall effect sensor is the silicon chip, and it's a high level of circuit integration. It leads to high reliability, but that silicon chip and that level of integration, that is subject to time. The industry likes to just keep improving and changing or whatever. So silicon chips that are specific, that they've made a specific model of a device that will sense using Hall effect, the Hall effect principle. That device isn't necessarily going to be around forever. Unlike a VR sensor that you can measure the amount of time in decades. A chip that's around a decade is an old chip, and so what we have to do is we have to constantly keep reinventing it. But the downside to that, well, the upside is that you get the latest technology. The downside is I can't tell you that it's been around for 20 years, because it probably hasn't. They build on the old technology, but it's a new chip, so you have to take that into consideration. All right, the typical output for a Hall effect sensor is a digital square wave output. The output is the amplitude. The amplitude is independent of speed. Unlike a VR sensor or passive sensor, the passive sensors we've discussed it's dependent on speed and air gap. It's going to get, as the speed increases and the air gap decreases, its output amplitude is going to change. With a digital square wave output, Doesn't matter how slow it's going, doesn't matter what air gap it is, that amplitude is going to remain consistent. That makes triggering a whole lot simpler. Typically, the single channel device is a 3-wire device, right? And we add another 2 wires for our direction sensing devices. So the 3 wires gives you a single channel of frequency. The bidirectional or the dual channel is a 5-wire device, and it allows us to sense not only speed but the direction of the target, whether it's going clockwise or counterclockwise. These things are great over temperature. They're good, you know, minus 40 to 125 degrees C. You'll see if you look at the passive sensors, that's a lot lower than the passive, but for most applications, this gets you into a very wide range. To understand the Hall effect a little bit, I have to kind of take the active series broken down into really 2 major categories. It's used, the single element is used in the RH series. And the RH series is, again, it's Hall effect. There's no need for alignment, but what you have is you have, you know, a basic schematic of the design. You have a magnet here with the 2 poles, and you have the chip laying flat on its back, okay? So that being said, again, there's one element, and you can kind of imagine if this is a center axis here, what we can do is we can rotate that, and it doesn't affect the performance of the sensor. And we'll go over, you know, comparing the different series together so you kind of give you an idea how to select one over the other. But the idea is with a single element, it really doesn't know the difference between a tooth or a valley. Inside, it's programmed with certain thresholds, but if you exceed those thresholds, it really doesn't know where to go. So with the RH series, it has to be maintained within that scope. As long as you do that, everything's fine, but if you go beyond that, you know, the difference between a tooth and a valley, it becomes a little bit difficult for it to discern. General speed sensing, great application, you know, that's great for the RH. But if you need a higher level sensor, you go to the differential sensor, and we use that in our BH and our DH sensors. What it is, it's a, as the name implies, a differential amplifier looks at 2 Hall cells, and it's looking for the difference in magnetic amplitude between the 2 Hall cells. So if you can imagine with a tooth positioned directly under that, with a tooth there, both of those Hall cells are going to be looking at the same field. If a valley is directly under those 2 Hall elements, the field is going to be the same. It doesn't really matter what the amplitude is, it's just the same. When they're the same, the net result is 0. It's only when there's a difference when this thing switches. So rather than switching on levels like on a tooth or a valley, it now switches on an edge, which gives it makes it more precise. And it also makes it much more resistant to things like runout. If you can imagine a target in an elliptical orbit getting closer and further away from your sensor, those changes in basic field, it doesn't really matter. It just could, because both elements are seeing either more or less, subtracts it out, and the differential will give you a much more stable signal under those conditions. When there's a tooth versus a valley, there's a difference, and that difference is always measured and can always be accommodated, and the device will always switch. Another element really to talk about quickly is when you look at the BH and the DH sensors, they use an automatic gain control circuit. And that allows us so that when the sensor is powered up, the sensor will measure the ambient magnetic field that's available to it. So you flip the switch on, power, the sensor comes up and it starts looking. Within the first 3 edges, the sensor calibrates itself to the ambient magnetic field. So where you would for each air gap, each one of these traces would be a different air gap. What it is now all of a sudden the automatic gain control makes the signal identical no matter what the air gap is. So it's always switching from the same points. So it reads, it calibrates, it understands, and then it optimizes itself to the particular target that it's looking at. Logic thresholds. It's important to understand some of the basic components of a square wave and really how it interacts. actually the title on this slide is tachometer application, and we talk about that a lot with the tachometers, just in terms of what the tachometer has to do in order to determine if there's a valid signal. So each signal has logic thresholds, and there'll be a logic high and a logic low. Those points define or allow the tachometer, our tachometer, or really anybody else's device that's looking at it at a pulse, it allows it to define that there's been a valid pulse. The greater the distance between the upper limit and the lower limit, that's the noise margin. That noise margin, the further it is apart, the less noise will affect the operation. And again, you can imagine on these logic levels, the high level and the low level, if this noise were to increase to the point where it went beyond these logic levels that we're switching off of, if that noise were to go beyond that, it becomes a problem for the device to know, well, was that a valid pulse or not? So the further you put those apart, the higher the amplitude can be of the noise, and the more solid you can get with the signal. All right, and the ability on the tachometer, I'm kind of going into a different module right now, but the ability for the tachometer to be able to program its thresholds allows then to have a higher noise margin and a greater ability to reject noise. Okay, so promised you this chart that compares the RH, DH, and BH. Those are our three main series. The RH is the rotational Hall, the DH is a differential Hall, and the BH is a bidirectional Hall. So you're looking at the relative capabilities of each. If you're looking for zero speed operation, standard gear 2 sensing, general noise immunity, any one of them will be fine. The RH tends to be the lowest cost, so that would probably be your best option. If you're worried about or worried about having to align it, and you don't want to have to align it, a rotational alignment, then the RH series is the clear choice here. But if you want fine-tooth capability, so if you want to go down below like a 32 dimetral pitch, if you have a target that is not a nice repetitive pattern, so if you have a single tooth like a keyway or a valley or irregularly drilled holes or anything like that, the DH and the BH series really do better for you. The DH and the BH give you a better air gap. So where you might be limited to, maybe 60, 70, 80 thousandths of an inch on an RH, and certainly 60 thousandths on a variable reluctance sensor, you can go 100 thousandths plus. You might even see with the right target, you might be 150, 200 thousandths of an inch. So if air gap's important for you, you've got to go to the DH and BH. When you get into, beyond general noise immunity, if you really want it, hardened to electromagnetic interference, the DH and the BH series are designed specifically for that environment. They both have high tolerance to run out. We're talking they're differential designs, and therefore intrinsically they are better in that kind of environment. The DH and the BH are self-calibrating. Both of those will, when on power up, calibrate themselves to the magnetic signature available at that time and every time thereafter. So it's not just a one-time thing. It's constantly calibrating itself and updating. The RH has a basic calibration scheme, but it's not as sophisticated as the DH and the BH. And one other thing, temperature sensing. The DH series has an RTD built into it on certain models, and that would give you ability. It's not meant for particularly accurate or particularly high speed, high sensitivity type applications, but if you want to know a basic, temperature and trend or whatever, those devices will allow you to take both temperature and speed measurement with a single installation. Our Hall effect sensors are offered in two different output styles. We have TTL compatible and supply tracking. The TTL compatible is this guy down here, and really if you get into it, the basic difference is a Zener diode that clamps the output to 5 volts. TTL is transistor to transistor logic. It's an industry standard, really known as like 0 to 5 volts. There's specific thresholds involved in that. It's a good solid platform, but if you want the greatest noise resistance, you'd want to go to the supply tracking. That allows us, as we discussed in that previous slide, where it shows if you can increase the output amplitude of the signal, then you gain a greater noise margin. And you do that because it's a supply tracking sensor, as the name applies. The output amplitude basically tracks whatever you're applying it. So if you're running a BH sensor on 12 volts, then you'll get essentially 12 volts out. If you run it on 20 volts, you'll get essentially 20 volts out. Whereas with the TTL, no matter what you're driving it with, you're going to get a 0 to 5 volt signal. And that allows, again, the supply tracking allows a slightly higher level of noise immunity. One disadvantage, the supply tracking, it's more sensitive to high capacitance. All right, and high capacitance is usually found, if you have long cable runs, or capacitors hung to eliminate noise. Those high levels of capacitance, if they're bad enough, they can actually keep the sensor from switching. And we have a device to help you out with that, and we'll discuss that I think in the tachometer and accessories module. Of course, every sensor has pluses and minuses, and the Hall effect is no different. They run on we'll call it a high temperature range. It's a reasonable temperature range, minus 40 to 125. If you want to go up to 165, they will run, but we test them to minus 40 to 125 to run a lifetime. And so if you're looking for a lifetime, then keep it within that range. If you run at 165, the junction temperatures will increase in that Hall effect device, and eventually they will fail. Exactly when, I don't know, but they'll run, but you don't get the life out of them. They run on a wide range of supply voltages. Most cabinets, or most installations will have something between 4.5 and 24 volts, or that's for the single channel, and 10 to 28 volts on the dual channel. The two output options, supply tracking or TTL compatible, allows you to kind of select and get the right benefits that you need. Much better air gap capability over VR sensors. Again, where you're looking at maybe a 60 thousandths max on a VR sensor, you can go out maybe 150, 200 thousandths with the right combination of target and sensor, active sensor. The output signal will react to the lowest increment of speed without loss of amplitude. So that's why we call them a zero speed sensor. And a lot of devices, they are moving slowly, and this is important. This is not a place for a VR sensor. You couldn't take a VR sensor and run it in such low speeds. So that becomes a decision point when to pick an active sensor over a VR sensor. Highly noise immune, highly vibration immune. Some other benefits, they install very easily. There's no alignment for the RH series, but the BH and the DH, because they're a differential sensor and one element needs to see the signal before the other, then there is an alignment. If you're used to our old H series sensors, it's the same as that. Highly reliable, but not to the same level as a passive sensor, which has decades of experience. Direction indication. On our BH series, we can then not only tell you what the speed is, but what direction the target's spinning in. And this last bullet item, this is not a challenge, but you can miswire the sensor. You can reverse the plus and minus leads. It says minus 30, but it's probably hundreds of volts really. But again, it's not a challenge, but people, when they get these devices, sometimes they get miswired, and so it should protect itself for the most part. Some limitations. Temperature, when you look at it relative to a passive sensor, you're not going to get 1,000 degrees out of this. You're not going to get 200 degrees C out of this for very long. So it's a feature and a limitation all in the same go. This last bullet item, not good with axial trajectory targets. That's just really an interesting way of saying, on an application where you might use a prox sensor, where you have a sliding member and then it's approaching the tip of the sensor, in a linear fashion, moving towards it or away from it. We don't do that well, especially you could see with a differential sensor, it's not going to do that well. What we need to do is to see target tooth or the feature on the target traverse, slide from one side of the sensor face to the other. That's how our sensors are activated. It's really a hallmark of speed sensing. So we're speed sensors, not proc sensors. Some family photos, we talked about single channel and dual channel, the RH series, and you can see the sensors are offered in all kinds of different, outlines, if you will, threads, round bodies, hex bodies, connectors, wires, cables, that kind of thing. So, they're all blind end sensors, but again, there's numerous lengths and sizes and everything to fit pretty much every application. There's even a 3/8 version. So we go 3/8, 5/8, and 3/4 are the typical sizes that we have. Working air gaps about 5 to 70 thousandths. When you look at the dual channel, the bidirectional series, the BH series, again, if you didn't have a part number on there, you might not necessarily know the difference between a dual channel and a single channel, except for the fact there's going to be, 5 wires coming out of it or 5 pins on a connector, and it's a different connector than that we use on the single channel. But again, the same types of variations in thread length and housing style and that type of thing. We're calling it new here. It's actually a couple of years old at this point, but it's worthy of mentioning as being a relatively new technology. And this, like the BH, it's a highly sophisticated sensor. It calibrates itself, when you power it on, and it's a very powerful tool when you have some interesting applications out there. It's a much more precise switching output signal, and it's just in general, beyond a general sensing application, it is a better tool to have. And as we mentioned before, it has an RTD temperature measurement option available on certain models. As with the passive sensors, we offer some sensors with these hazardous location protection strategies. The two that we look at for Hall effect or active sensors, explosion proof and intrinsic safety, but only the non-sparking. It's not really a limited energy device, and it's not quite as all-encompassing line that we have with the passive sensors, but these get us into most of the applications. Intrinsic safety is a little bit more difficult with an active sensor, and so that hasn't been pursued at this point. Again, this is essentially the strategy is kind of laid out a little bit differently, so you can see, the explosion proof is a North American standard system using the class, division, and group system. And the intrinsic safety then goes to a.tek's, and it's a zone 2, so it's the lowest level of intrinsic safety, but it does not require a barrier to install. Okay, that's it for the active speed sensor module. Please, if you were looking for more training, then please look at the company introduction, the variable reluctance speed sensors, and the tachometers and accessories module. Thank you.